Yes, so we have a newcomer this week. Renberg, would you like to give a brief introduction of yourself?
Hello, everyone. Yeah, I'm excited to be here. So, I'm a junior student for applied maths at UC Berkeley. Yeah, and I really like deep learning and machine learning. I was doing a lot of online courses. Yeah, very exciting. Yeah, that's all.
Okay, okay, thank you. So today, Robin, Renberg, and me will give presentations. So I think I will go first. So I will share my screen with you. Sorry, seems there's some technical issue. I will rejoin the meeting. Okay, can you see my screen now?
Yes, we can.
Okay, great. So yes, last time Jing has introduced the gradient formula here for us. So I have added a note to for the derivation of the formula. So you can see here the gradient of a scalar function f is defined as the unique vector field whose dot product with any vector v at each point x is the directional derivative of f along v. And this is the equation. You can see that the gradient and the dot product with v, and the right hand side is the directional derivative of f along v. And the directional derivative in direction v is the slope of the function f in direction v. Namely, it is the rate of increase of f per unit of distance moved in the direction given by v. And since we want to minimize the f, we would like to find the direction in which f decreases the fastest. So we can do this by using the directional derivative. So you can see in the equation here, we want to find the v, the unit vector v, such that the directional derivative of f along v will reach its minimum. And we can write the dot product as the product of the norm of two vectors and times the cosine of the angle between them. So since v is an unit vector, we can just substituting in that the norm of v is equal to 1. And we can also ignore the factor that do not depend on v, namely the norm of the gradient. So this simplifies to, we want to find the vector v that make the cosine theta to reach its minimum. So this is minimized when v points in the opposite direction as the gradient. And in other words, the gradient points directly uphill and the negative gradient points directly downhill. So we can decrease f by moving in the direction of the negative gradient. And hence we have the formula here, where alpha is the learning rate, a positive scalar determining the size of the step. Is there any questions for this part?
This is great. Do you have any visualizations of this on the map?
Yes, I have. Here, it is a example, yeah. So you can see that we want to reach the global minimum at x equal to 0. And you can see here the derivative of f is 0. So gradient descent halts here. And when we are at the right-hand side, for x greater than 0, we have the derivative bigger than 0. So we can decrease f by moving leftward. And while we are at the left-hand side, we have the derivative smaller than 0, and then we can decrease f by moving right hand. So we are just decreased in the negative direction of the gradient. Yeah. Is there any other questions?
Do you have any discussions about the speed of convergence to the optimum in depending on the distance from the optimum?
On the convergence of gradient descent.
Right.
I haven't that part.
So if anyone is interested in working on the convergence rate, that would be an interesting topic. Also, the other interesting, so because like there are algorithms that pass the optimum threshold and then they return. And so it's interesting to compare this rate between the algorithms. The other interesting topic to study is basically what happens when we have multiple optimas.
Oh, okay.
Multimum optimum points, and whether it can find the global optimum or not. So local convergence, basically.
Yes, I think that can be the next topic we can cover in our meeting.
Great.
Yeah. If anyone is interested to present about this, you can update it in our records of presentation spreadsheet in our private channel. Yeah. So I will move on to the mini-batch gradient descent. So if you have a huge training set, you have to process your entire training set before you take one little step of gradient descent. And then you have to process your entire training set again before you take another little step of gradient descent. So it turns out that you can get a faster algorithm if you let gradient descent start to make some progress even before you finish processing your entire training set. And in particular, you can split up your training set into smaller, little baby training sets. And these baby training sets are called mini batches. And here is a simple example of mini batches. if you have a huge training set with 5 million training samples, and let's say each of your baby training set have just 1,000 examples each, so you can take the first mini batch as the first 1,000 elements in the training samples, and then you take the next 1,000 samples, and so on. So altogether, you would have 5,000 of these mini batches, and then similarly, you do the same thing for Y. Hence, we end up with mini batches x, t, y, t, where t can be any integer from 1 to 5,000. And for the algorithm, for t equal to 1 to n, where n is the number of mini batches, namely for each mini batch, x, t, y, t. Firstly, you can perform forward propagate on x, t, and then you compute the cost function jt, and then back propagate to compute gradients with jt using xt and yt. And next, you can update the parameters with the mini batch gradient descent. So this loop is one pass through your training set using mini batch gradient descent. It is also called doing one epoch of training. And epoch is a word that means a single pass through the training set. And if we choose the mini batch size to be 1, then it just gives the algorithm called stochastic gradient descent. And in this case, on every iteration, you are taking gradient descent with just a single training example, xi, yi. So the equation looks like this. So here is a comparison between the batch gradient descent, stochastic gradient descent, and the mini batch gradient descent. So you can see here, the blue line is the batch gradient descent. It takes relatively low noise and relatively large steps, and you could just keep matching to the minimum. However, it may take a long time to process and need additional memory. While for the stochastic gradient descent, we have just introduced, it has the batch size 1. It is easy to fit in memory and efficient for large dataset. It is the purple line here. However, it can be extremely noisy since sometimes you hit in the wrong direction if that a training sample happens to point in a bad direction. So it won't ever converge and will always just kind of oscillate and wander around the region of the minimum. So in practice, mini batch gradient descent with batch size between 1 and n works better. So it is shown as the green line here. It's not guaranteed to always head toward the minimum, but it tends to head more consistently in direction of the minimum.
So there is something very important to mention here. So this comparison also depends on your use case. If in your use case you have a long time available for training the model and it will be used forever, then so it's better to use the batch gradient descent. On the other hand, if you're using if your training is incremental, meaning that while the neural network is being used in the application domain, it is also receiving new data points to be trained with, then batch is not an option at all. You have to choose one of the other options. And depending on how fast you want to train, there is a trade-off between the speed of training and the noise that you enter into your model. Based on that trade-off, you can choose between the two options.
Yes. Thank you. I think I can update the choice of the batch size. after.
These are very great notes. Thank you.
Yeah. So I think that's all my part today. Is there any other questions or comments? Okay, great. So I think we can move on to Robin.
Okay, like I will begin to present now.
Yeah.
So like, can you guys see my screen now?
No.
Okay, I will try again. So does it work now?
Yeah.
Okay. Yeah, so like today I will talk about two concepts, and these two all belongs to the optimizer algorithm. One is the exponentially weighted average, and another is the gradient descent with momentum. So the first one is not actually an algorithm itself, but it's more like a strategy or concept that's useful for the for many optimizer algorithms. So I will begin with this part. So exponentially weighted average is a technique frequently used for time series data. So by taking the average sum of a previous data, you could smooth your data series and get an approximate trade of it. So the below part is the math behind this method. So imagine you have a series of data points theta 0 to theta n, and our target is to compute another series of data point from t0 to tn that can approximate the trade of the original data points. So for the initial time t, when t is equal to 0, you assign the theta 0 to v0. And for the other data point, you actually get a weighted sum, a weighted average of vt minus 1 and theta t. And beta here is a parameter, is from 0 to 1. And in practice, we will like assign it to a very large point, like 0.9 or 0.98. And if we expand the second formula, we can like get a better sense of what it means. Like we can, since like vt minus 1 is equal to beta vt minus 2 plus 1 minus beta theta t minus 1, we can plug it into our equation and we continue to expand it. We will get like the third equation here. So it is actually a weighted average of all the data points from t equals to 0 to t. And since like beta is a number less than 1, so when every time you multiply beta, you will get like smaller and smaller weights. So we will assign smaller weight to the data points that is away from our current data point. And making use of this formula, you can and if we denote wi to be the weight we assign to theta I, we will get this equation. So it means that when the data point is 1 over 1 minus beta away from our current point, the weight of it will be 1 over e times wt. So we are approximately averaging over 1 over 1 minus beta days when calculating vt.
This is very helpful. Any questions about how we derived the formula? Is there any questions? Great. Please continue.
Okay. Yeah, so another concept related to it is the bias correction. So from the previous equation, we can see that if we are averaging a data point that's very close to t equals to 0, we are actually averaging a very limited numbers of data point. So we actually will get some bias because of that. And this term can help to correct it. But actually in practice, a few people use this to correct the bias. Most people just like ignore this bias. And this part is like an example of this exponentially weighted average. It might give you guys a better sense of way it works. So this figure, the blue dot here are the actually data points. So the theta 0 to theta n as mentioned before. And the red curve and the green curve are the exponential weighted average with different beta value. So if we assign beta equal to 0.9, we will get this right curve. And if the beta gets a little bigger, 0.98, we will get this green curve, which is smoother because like basically we are averaging over a longer day period. So we will get like this curve. And like this is all about exponential weighted average part. Does anyone have any question about this part?
So just to make sure everybody is on the same page, please carefully think about how we can trade off between bias and variance of the model by assigning different values for the parameter beta. This is very important. Like bias variance trade-off in machine learning is in general very important. In this case, we are playing with beta.
Yeah.
Just think about like how to like what you should do, what you should do with the value of beta when you want to have more variations, when you want to increase the flexibility of your model to like fit more diversity in data. In comparison with the case that you want to reduce overfitting and you want to have less variation in data because you don't want it to be biased, you want to reduce overfitting. Think about how you can play with the value assigned to beta for this trade-off.
Okay. Like, do you want me to add a note about it, like after this part?
Sure. If you can show like with two examples of where we want to reduce overfitting or when we want to like make it better fit to the model, like the trade-off between bias and variance, that would be very helpful.
Okay. Yeah, I will try to do that after the meeting.
Also, we have notes about bias and variance in machine learning in general, like the general definition. I feel like it's a good idea if you define those as parent nodes of this. Like just link these to those nodes about variance, bias, trade-off, and machine learning, so that if anyone has difficulties understanding those would be the prerequisite to continue with this example.
Okay.
Thank you.
So like I will continue to talk about another concept is like gradient descent with momentum. So like the basic idea between these is to compute an exponentially weighted average of your gradient and then use that gradient to update your weights instead. It almost always works faster than the standard gradient descent algorithm. So we can like see the implementation detail of it. So on the iteration t, you will have these three equations, and the third equation is very similar to the one mentioned in the mini-batch gradient descent implementation. So, but instead of just subtracting alpha times the gradient itself, we will subtract the VDW and VDB. And this two is actually just the exponential weighted average of your gradient, like in the first and the second equation. So now we will have two parameters. One is alpha, is the learning rate, and another is the beta, just as I mentioned before, is in the exponential weighted average part. And the intuition between the gradient descent with momentum can be explained pretty well by this figure. And you can see like the red curve here is the gradient descent part. You will have many up and down, like many oscillation because you are updating your models based on a small batch of data set. So you will get close to your optimized model, but in the process, in each iteration, sometimes you will get better model and sometimes you will get worse model. And the gradient descent with momentum does, like, it can help to averaging out the positive and negative oscillation in the vertical direction. But like, since all gradient points to the same direction horizontally, the result in the horizontal direction will remain large value as well. Yeah, so that's all about this part. Does anyone have question about it? Okay, I think it's all about my presentation today. I will like stop sharing my screen.
Thank you. This was really helpful.
Yeah, thanks, Robin, for your presentation about the exponential weight average and gradient descent with momentum. So maybe next we can move on to Rimback. Rimback, are you there?
Yeah, I'm here. I'm trying to. Can you see my screen right now?
Yeah.
Yeah. Okay. Let's go. It's my first presentation, so tell me if I'm doing anything wrong or. Okay. So I saw like this list of the optimizers. There were like there's actually like a lot of optimizers. I just added like 2 also. So let me go with the first. Let me talk about. So we just talked about the momentum algorithm. So momentum algorithm, we keep the momentum, which is weighted average of the previous gradients. We go into direction of momentum, and then we go in direction to the current gradient, like kind of so. And Nesterov momentum is similar, but in a way, like first we go in a direction of momentum, we recalculate the gradient at new point, and we move into new gradient. So usually, let me show you implementation. Show me the formula. So that's the formula. This looks a lot. I forgot about. Yeah, this looks. Wait, I'm sorry. This looks a lot like a momentum formula, but like the difference is that instead of parameters. Wait, what is that? What is happening? I don't know what.
So when you
So yeah.
when you click each formula, it shows the code behind that formula. So if you click somewhere else on a piece of text, like in the middle of the node.
Oh yes, yeah. So as a step, I like as a step at the timestamp t right now, I represent the momentum, and the whole like the step that we need to take. And the only difference is that we recalculate the gradient at the different point. And usually this works. So usually in practice, this algorithm works a bit better than my momentum method. And let me show how it might be working better. So I drew a small picture here, and let's take the example. So let's talk first about the how like momentum would go. Imagine this is like the global minima for the cost function, and the red point is where we are like at the where we are right now at the cost function in terms of our parameters. So yeah. So let's say we like first in momentum we are at this point. We move a bit already to the edge of this global minima, and then we already have some momentum here, and we move in the direction of momentum, and it happens to go down. But now we have to go in the direction of the gradient from that point, which is actually very high. So we actually can go out of the, or we can go like, we're not gonna stay at the minima. We can go out, and there is also might be a bigger gradient, and we actually might diverge. Where Nesterov algorithm would say we moved from to the edge, and now we move to the momentum down, and now we can recalculate gradient at this point, which is very small, and we're not gonna move almost. And we actually going to converge faster. So in this way, Nesterov algorithm, it's a bit more intuitive than momentum algorithm. Yeah, I also was searching about the implementation of Nesterov algorithm, how it's done, because we have to recalculate the gradient, but we usually get only the gradient at the current point, and we like usually, like I say, in libraries like TensorFlow, we don't have ability to recalculate the gradient for like a different point. So yeah, it was hard to find. I'm still searching about it, but I think in TensorFlow it's implemented not exactly, but the estimation of different gradient.
Thank you for adding this note. This was exactly what I was looking for when I asked for analogy for the convergence rate.
Yeah, I was searching a lot, and like I couldn't really find like implementation. Yeah. So then one of the main cons of the Nesterov and momentum that both of this algorithm depends a lot from learning rate. And like in ideal, we actually want a like optimizer that we don't have any additional hyperparameters. And the learning rate is a very important hyperparameter. So this way we can come to adaptive gradient algorithm. So in adaptive gradient algorithm, instead of like we are taking out the hyperparameter of learning rate, and we're actually changing the learning rate as we go. Let me show the mathematical implementation. So as I can see with the helper matrix, so sorry. Yeah, as you can see, with the help, the W is our like the parameters. It's also the same thing we will apply to bias parameters. This is like just the weight. So this is the G. It's like our helper matrix, and it just sums up all the squares of previous gradients. And as you can see now, our learning. This is also just to note. This is gonna be all the like point-wise matrix multiplications. Yeah. So this is a matrix. So yeah. So now our learning rate will like decrease and adapt to our current like how as we go, because now with learning is a changing variable. So yeah. So that's the implementation. The W is the parameters. We have to pick starting learning rate, but now we don't really have to care a lot about that. And usually it's something around 0.01. Never mind about that. Change it. And the epsilon is just the epsilon here is just to avoid division by 0, because maybe it can become 0. Yeah. So and
this is really helpful, but I want you to for the future, I want you to add more explanation to your notes. So notes on One Academy are not like the slides. So you need to add enough explanation to make them understandable. And I don't know exactly why you added that last line in the previous note, but I feel like that is a formatting issue. So
last line, which one? This one?
the line that you say, also the same process is done, and here you say the same principle applies to the bias parameters. So
yeah, because
you have defined it as code. That is not supposed to be code.
okay.
So let's click the pencil button. Let me quickly show you.
The edit button, right?
Yeah.
Okay, let me.
So propose an improvement on the node. So you see that space, just get rid of that.
Okay.
And you can add an enter, right?
So yeah, let's discuss pros and cons of the adaptive gradient algorithm. The main advantage is that we don't really need to care about learning rate because it changes by itself and changes as we want. But the main cons of this particular algorithm is that we stacking bunch of squares of gradients, and with time the matrix can become very, very big, and the learning rate now, because of that, the learning rate will become very, very small, and we're not gonna like learn, we're just gonna be stuck at one point. Yeah, so now to solve this problem we have a very similar algorithm, which is RMS propagation. It's a very similar, but it's adding to the weighted average of the gradients from before. Also wait, I forgot about to talk about the Python implementation of the adaptive gradient algorithm. Sorry, this is also formatting issues. I don't know, like, so there's import numpy SPS class, like, so yeah, you can check later. This is let's say it's a class for adaptive gradient. It's like how it's supposed to work. It's like attaches for a layer in neural networks, and it keeps inside the variables for the G matrix. And there's a function which is get steps, which we have to put the gradients of the weights and current gates of the biases, and we get the steps we need to subtract. So yeah. So this
Just to make sure we're on the same page, there is no formatting issue here. So you have added a code snippet and you have correctly formatted it.
Yeah, but you see over here now, like this is like a text and this is like a code. It just feels weird.
But okay. For that, you need to add the indentation, and you can put it in backticks. You can put it in backticks, like you know where tilde is in your keyboard. So the same key on your keyboard is for backticks. So you, in general, on the web, when you want to add a code snippet, you put it in backticks.
Okay. Can you text me? I cannot hear you normally right now. Maybe.
So just send me a message on Microsoft Teams after the meeting. I'll be able to show you how to do that.
Yeah. So if you wanna, So generally, if you wanna check the Python implementation, you can click it here. So now it's back to RMSdrop. It's very similar. So, yeah, it's very similar, but now it's adding the beta variable, which is works for the weight average. So with the beta variable, it's gonna, like, with time is gonna go to 0, and we're not gonna be stacking bunch of squares of gradients, and it's not gonna go to 0 quickly. So yes, the advantages are the same, but now it's getting rid of we are getting rid of this problem, which goes to the vanishing gradients, which just become not vanishing gradients, but vanishing learning rate problem. And also you can see here the Python implementation that also has like the same problem here. Yeah, so it works the same. It just keeps the G matrix variable inside, and it has the same function, get steps. It takes the grads for weights, grads for biases, and returns the current step for biases and weights. So we can update them. Yeah. So now we talked about so far we talked about only like two kind of ways, two approaches for the optimizers. One approach is use the momentum of previous, how we like were. It's like a ball from on a cost function. It's just rolling down. And another one is adaptive learning rate. So what if we just combine these two methods? And by combining this the momentum method and RMSdrop method, we get Adam. As you can see here, this is mathematical implementation. So now instead of one helper like matrix, we have two helper matrix. One is for helping to shape our learning rate, which is here. It's very similar to the G matrix. And this is M matrix, which is very similar to the momentum matrix. And as previously was explained, at the beginning, there were introduced some biases. So the authors of the Adam noticed like a bias at the beginning when it was without, and they had to add this 1 minus beta to the power of t and over here to get rid of those biases, as was explained previously before me. So yeah, and as you can see here, this can supposed to be part of RMS, and this is part of momentum. Yeah, I'll switch all the I'll switch all the problems with formatting and stuff. Yeah, the main pros and cons is this algorithm combines like the two approaches, and it usually works better than both of the two approaches. But recently I saw one paper that says maybe we need to also consider just a usual stochastic gradient descent, because one paper I was reading, it was talking about how it generalizes the SGD generalizes better than those algorithms like Adam and RMSdrop. Just generalizes over like over the validation data and everything like better than those algorithms. I'll add it later. I didn't have time to.
Yeah, please create reference notes for those papers, especially what you're saying about Adam. I'm interested in taking a look at that. So please add reference notes for those papers so that if anyone wants to follow up with them, they can just do that.
Oh yeah, I'm sorry. Yeah. So yeah, over here you can see the same principle of implementation for the Adam. We have here the 4 inner variables for the M matrices and V matrices for bias and weights, and yeah, we over here just like implementing the formula in NumPy. Yeah, that would conclude my presentation. Please say if you have any.
I also suggest you to add relation nodes between these to compare and contrast these 3 algorithms with each other.
Relation nodes?
Yeah, so a relation node is to compare different concepts.
It's comparing different concepts. I see.
Right. So you define a relation node to like compare or contrast or talk about similarities between the two concepts or like categorize them in different groups.
I see. Okay. I see.
Right. For your first presentation, it was impressive. Thank you.
Okay, thanks.
Sorry, I have a quick comment. That is for all the nodes you have already proposed. Please add a reference node. So you can just create a reference node with the website in it, and then for each node you add a reference node as the node you created.
So I can just like create a reference node with a link inside and like reference all the nodes to the node, right? You mean that? Okay.
You know how to add a reference node for the other concept nodes, right?
Or I can also with propose with this, right?
Yeah, you can click it and
yeah, this one, right? Okay.
Yeah, that is to create a new reference node. And after you create one node, then you can just click edit or improve this node.
Okay. Thank you.
Yeah.
Yeah, that would be it.
Do we have other presentations for today?
It seems there is no.
So in that case, I think, please share your screen again. Rambek, please share your screen again. Rambek, do you hear me?
Can you see now? I was muted.
Yeah. So if we don't have any more presentations, let me just quickly show you how to create reference nodes and cite them,
Wait,
so that
wait.
everybody can see how to do that for their future presentations.
So
So find one of those papers that you have used here on Google Scholar. Just go to Google Scholar, find the reference you were talking about.
Wait, Adam.
You need to search that on Google Scholar.
Google Scholar, okay. Wait.
Don't worry, take your time.
Okay, let me Google it. I think I'll just get some. Then I'll just refer to it.
Sure.
Yeah, I think this one. Yeah, it's like improving generalization performance by switching from Adam to SDG.
Great. So just copy the title and the authors into Google Scholar to find the correct citation for them.
Okay.
So you have Google Scholar open in the other tab.
Oh, okay. I see.
Great. Now you don't need to click that. Go back. Go back. Yeah.
Yeah.
So you see below this it says cited by. Next to that on the left, yeah, that is what you need to use. Click that, please. Cite. So here you can find APA. No, APA.
APA. Okay.
Yeah. So you need to copy that APA. Now go back to One Academy. So where have you used the content of that paper?
Adam. Here.
Great. So below this, you see the node has one tag but no citation. See that? So there is no citation. So you need to add a citation so that if anyone wants to follow up with what you have added, they can easily do that. So click edit. You want to add the reference first? Sure. Click reference child node. And so on the title, please add the title of the paper.
Title of a paper, right?
Yeah. You can just copy it from the PDF file or Google Scholar. Great. Now, propose it, please. And you can add more tags if you like. So right now, your default tag is data science. If you like, you can add more tags to make it more specific. But for now, that's fine. Now, in every node that you have used content from this paper, you need to cite it.
I have to like put cited existing preference, right?
Exactly.
I see.
You need to add the page number. No, don't propose it. Let's do it again.
So
you need to add the page number. Like, which page of the paper did you find what you have added to this node?
I don't remember.
So
that you can just add the abstract, like first
you
page.
need to help others to figure out where to find the information so that they can follow up with that.
Okay. But I guess it's just like conclusion.
Sure. If the whole paper is introducing Atom or it's about like an overview of Atom, I would just put the first page, like the abstract.
Okay. So it's like first page. Right now, like this?
I would write page 1 so that it shows on top. You see what happens when you type it?
Mm-hmm.
So it shows on top of it, right? So colon page 1. Great. So propose it, please. And also add it to the other nodes where you have used the content from that paper.
Oh, okay.
Is there any node here that you have used that paper for?
Not really. I used this paper just to talk about how the Atom might generalize words in SGD.
So where did you get the Python code?
So I wrote it myself and tested.
Got it.
I
didn't use any papers to understand how to write that Python code?
I used the articles and yeah. And
what is that?
I used an article.
Yeah, so you need to cite that article as well.
Okay.
Thank you.
So should I do it right now?
Yeah, one last thing. Yeah, so you see you have added reference right there. So you shouldn't do that. You should define that reference in a reference node and cite it everywhere you're using that reference.
Okay. Yeah.
Thank you. And one last thing. So in terms of your Python code, can you open one of those nodes with Python code?
Let's see. Wait, where is it? Yeah. Here.
Great. So edit that, please. Now, on top of the code, please add on top, very first line in the beginning. So add an enter. Yeah. So add 3 backticks, like the tilde button, backtick.
What is this button?
It's similar to quotation, but it's kind of like diagonal.
Like this?
Can you zoom in? I cannot clearly see that. No, these are simple quotations. These are straight quotations. You need to use backtick, like on the left of number 1 on your keyboard.
Like this?
No, these are tilde, the same but without shift.
This one.
These are all backticks, right? So you need to put it at the end as well.
Yeah.
So for code snippet, you need to use backticks. Right. So now, if you propose it, you'll see what happens. See how it turns out? Yeah. Now, there is one more thing you can do here. So return to the like edit mode, right? So after the first backtick, add the word Python. Immediately after that, Python. I think it should parse it. Let's try. Yes, it understands Python.
I see. Okay.
Good. So if you add like R code, you can add like backticks R. If you add like JavaScript, you can add backticks JavaScript.
Yeah.
Propose it, please.
Can I add like a reference to a GitHub because it's in my GitHub?
Sure, definitely, yeah. So every node should have a reference assigned to it, like a citation.
I see. Okay, I see.
Unless you want to add like an idea. For that, you have to use idea type, like idea node. If you want to add an idea so that the rest of the team can read your idea and evaluate it and give you feedback, like an idea for a new algorithm or whatever, you can use idea nodes.
Okay. I see.
Thank you.
I'll add the reference.
Okay, thank you, Renback and Iman.
Can I stop presenting?
Yes.
Thank you.
So I think there is not no more people to make presentation today. So just to make sure that everyone is working on something, So Nikis and Aryan, I just want to know, is there any topic you are now working on throughout this week?
Yeah, I'm working on orthogonalization right now. Yeah, I can present on that next week. I just forgot to put it into the form that you made.
Okay, great. So please update these information in our spreadsheet. Okay, thank you.
Yeah, I'm working on learning rate decay.
Okay.
I was going to present, but my laptop is in the shop. I'm talking through my phone and I can't present from this.
Okay, great. Do you think you can make it for next meeting?
Yeah, I can present next week.
Okay, so please also update the information in our spreadsheet.
Okay, I'll do that.
Okay, thank you.
Can I ask a question?
Yeah.
Can we add like the deep learning nodes, maybe which are not covered in a specialization?
Yes, you can.
Okay.
But please cite that. Yeah.
Yeah, I'll cite.
So please cite the textbook because it is difficult to find citations from Coursera courses. So whatever you have in data specialization in Coursera courses, that is also written in the textbook by Professor Ng. So you already have access to the textbook, right?
Yeah, I requested today.
Yeah, so they will give you access very fast, actually. So you can just use the content from the textbook and cite it from the textbook, not from the Coursera courses.
Oh, okay, I see.
Thank you.
Yes, we have already got this reference note. You can just search for deep learning specialization, and you will see our reference notes for the textbook and also the Coursera videos. Yeah.
Okay, I see.
That is very helpful.
Okay, so I think that's all for our today's meeting. So have a good day, everyone. You are free to leave now.